Okay, so chapter 9, we're going to be talking about transforming our data that may, or our scatter plots that may not appear to be a linear pattern, and we're going to try to transform it using certain functions in order to make it, pretty much, make it a linear pattern. Okay, so we know how to describe two variable relationships that show a linear pattern. So the problem is if it's curved, we wouldn't know how to approach that. But if we can change it, then we might be able to. So when two variable data show a curved relationship, we must develop new techniques for finding an appropriate model. So this chapter is going to describe several simple transformations of data that can straighten a nonlinear pattern. Once the data have been transformed to achieve linearity, we can then use what we would normally do and use a least squares regression to generate useful model for making predictions. We can see how well that regression line fits, etc. So applying a function such as a logarithm or square root to a quantitative variable is that would be called transforming data. Okay, so we will see in this chapter that understanding how simple functions work help us choose and use transformations to straighten nonlinear patterns. Okay, so this is it's a scatter plot that's providing data on the health and well-being of the world's inhabitants. Okay, so it's the individuals are of the world's nations for which they gathered from only what they had. The explanatory variable is a measure of how rich a country is, and its income per person, or based on income per person. The response variable is the life expectancy at birth. Okay, so for a certain extent, we definitely expect people in richer countries to live longer just because of, they have better access to medical care, they have more access to medicine, they typically probably lead healthier lives, they have healthy water, sewage systems, they have better food, they're more educated about what they eat, how they live their lives, exercise, things like that. So we're not kind of surprised that we see definitely a strong relationship happening in this graph. But the problem is that the overall pattern is not linear. Okay, so it kind of sees, like, you can see the life expectancy rise very quickly as income per person increases, right? But then it starts to almost level off, right? So people in poorer countries might live just as long as wealthier countries, but it's kind of those extremely poor countries that are almost not comparable, okay? So, like, for example, East Asia. So kind of like these greens over here and these light blues, right? So East Asia and the Pacific and Europe and Central Asia, okay? So they may not be as wealthy as the United States, okay? Although they are generally living the same life expectancy, okay, as opposed to down in red, so sub-Saharan Africa, which are significantly, poorer countries, are definitely not living where the wealthier countries or living the same expectancy lifespan as the wealthier countries, okay? You definitely have a few outliers here, so you have an outlier at Gabon, South Africa, Equatorial Guinea, and Botswana. Okay, so these countries, what did it say? Oh, these countries, so Gabon and Equatorial Guinea produce oil, where South Africa and Botswana produce diamonds. Okay, so they're outliers probably because they the wealth is probably going more towards just a few people than the country. Okay, so they're standing out per person income because of those few wealthier people because of those industries. But the life expectancy is still about the same because it's not, it's the mean, and the mean is being pulled up by those few wealthy people. Okay. Sorry, skipped right past it. Okay. So we would want to see more of a linear pattern for us to understand, if there's a true relationship, if it's a linear relationship, can we find a regression line to make predictions about if there's a true relationship being shown, okay? So we can straighten out that last scatter plot, okay, by using logarithms, okay? So the figure below plots the logarithms of the income per person as opposed to just the income per person. So it's the logarithm of the incomes, okay, and keeping the life expectancy the same. And what appears to happen is that your graph is now showing a clear linear pattern. Okay, so let's first discuss actually not logarithms, but we'll start with transforming with roots and powers. Okay, so when you visit a pizza parlor, you order a pizza by its diameter, say 10 inches, 12 inches, or 14 inches. But the amount you get to eat depends on the area of the pizza. The area of a circle is pi times the square of its radius. So the area of a round pizza with diameter x is as follows, right? So the power model of the form y equals ax to the p, with a being pi over 4 and p being 2. Okay, so we expect area to go up, right, with the square of a dimension. You would also expect volume to go up with the cube of a linear dimension, right? So geometry helps tell us kind of how to expect power models in some settings, okay? There are other physical relationships between two variables described by power models, such as distance of an object dropped from a given height, time, so that would be distance equals the height times the time squared, okay? Time it takes for a pendulum to complete one back and forth swing, so that would be the period for a back and forth swing would be time times the square root of the length. Okay, intensity of a light bulb is related to the distance from the light bulb. So all these things are showing power models, okay? Although a power model of the form y equals ax to the p describes the linear relationship between x and y in this setting, there is a linear relationship between x to the p and y. If we transform the values of the explanatory variable x by raising them to the power p and graph the points x to the p, y, rather than just xy, your originals, what you end up doing is now straightening out your scatter plot. Okay, so if it shows a curve, then you expect that there be a power model involved, changing your points so it's x to the p, and then plotting your same old y should have the effect of straightening out your curved pattern that you saw. Okay, you guys are not going to, I should have started with telling you, you're not going to be expected to know when to use a power model, when to use a logarithm, when to use an exponential. It will be told to you, so don't feel like that you should have to recognize when to use what. They will tell you that. Okay, so all right, so let's look at an example so we could kind of get an idea of what we're doing here. So imagine that you have been put in charge of organizing a fishing tournament in which prizes will be given for the heaviest Atlantic Ocean rockfish caught. You know that many of the fish caught during the tournament will be measured and released. You are also aware that that using delicate scales to try to weigh a fish that is flopping around in a moving boat will probably not yield very accurate results. It would be much easier to measure the length of the fish while it's on the boat. What you need then would be able to convert length to the fish's weight. Okay, so reference data on the length in centimeters and weight in grams for Atlantic Ocean rockfish of several sizes is plotted. Note that there is a clear curved pattern there. Okay, because the length is one-dimensional and weight, like volume, is three-dimensional, a power model of the form weight is equal to A times length to the third should describe the relationship. This transformation of the explanatory variable helps us produce a graph that is quite linear. So essentially, using the cubed power here, I was able to straighten out the graph, or they were able to straighten out the graph. So another way to transform the same data to achieve the linearity is to take the cube root of the weight values and graph the cube root of weight versus length. Note that the resulting scatter plot has also a linear form. So once you straighten out the curved pattern, so here it's just, as opposed to taking length, a times length to the third, they're taking the cubic root of weight, so it's really just showing the same thing. It's just, okay, you're changing the x as the inverse function of what you changed the y originally. So it's basically showing the same thing. So once you straighten out the curved pattern in the original scatter plot, we fit a least squares regression line to the transformed data. This linear model is now depending on whether we feel like it's a good fit or not. So we would check our S and our R squared value. Then we can use that model to predict values for the response variable. Okay. So let's go ahead and see how we would write an equation of the least squares regression line for the rockfish, okay, defining any variables that we use, okay. So, so the first transformation that we did was we cubed the length, okay. So it's still the same thing that it's been. So the 4.066 is your y-intercept found in your output, okay? This slope is down here, okay? So plus slope times your x, but your x here is where we cubed it, okay? So as an equation, it would look like that. For transformation 2, that was where we did kind of the inverse. So my y-intercept here plus my slope times my length. But the difference is that your prediction was the cubic root of your weight, okay? So you weren't cubing your x, you were taking the cube root of your y. Okay, so assuming that your R squared value is high enough and our residual plots show random scatter in both, so that's going to show us that a linear model is appropriate. Looking at my R square value of 99.8 and 99.5, I would say that it's accounting for most of your variation there. So I think it is an appropriate fit. So now we can use it to make predictions, okay? So for the first one, I'm predicting for the weight for 36 centimeters, okay? So just plugging in 36, and likewise with the other, you should see that you get very close to the same answers. Okay, we can interpret S in context. For transformation 1, the standard deviation of the residuals is 18.841 grams. Prediction of fish weight using this model will be off by an average of 19 grams. For transformation 2, S was 0.12. That is predictions of the cube root of fish weight using that model will be off by an average of 0.12. So realistically, if you had to choose, it does appear that transformation 2 is giving you a better prediction line, better regression. Okay, so I'm going to call it quits here for my first video.